I'm Dan Zimmerman. I'm from Galois, and thank you for the nice things, Richard, that you just said about us. I'm going to talk a little bit today about formal assurance for RISC-V implementations, including what formal assurance is. This is joint work with Joe Canary and a whole bunch of other people, both inside Galois and elsewhere. And it's partially supported by DARPA, which is the reason for this large disclaimer here. So just a little bit about us. Galois was established in 1999, and the basic idea was to take the expertise that a bunch of professors at the Oregon Graduate Institute had in functional programming and formal methods, and apply it to problems of information assurance, mostly cryptography, and mostly verifying cryptographic algorithms. Today, we have over 40 active projects for a bunch of different clients, some within the US government and some commercial. And we can talk about those offline if anybody is interested. And over the years, we've broadened our scope from cryptography to basically high assurance, everything having to do with computing systems. So people come to us with hard security problems, or they want to know that their new algorithms actually do what they say they do, and we help them find these things out. So before I talk about what high assurance means, let's take a second and consider the many definitions of RISC-V. We've heard a lot about some of them over the past couple days and over the past workshops. So there is, of course, a RISC-V instruction set manual, which defines all the different RISC-V ISA flavors in a fashion that you can read and then you can go implement. There are many mechanizations of RISC-V, lots of software simulators. We've heard about a couple of those over the past day. And then there's also various abstraction levels for those simulators. So like GEM5 is a cycle-accurate simulator. The stuff that Imperis showed is a fast simulator that is not cycle-accurate, but also gives you good information. And there's also lots of handwritten RTL out there, all of the different RISC-V implementations that have been done in System Verilog and Verilog. There's also a bunch of handwritten higher-level hardware descriptions out there, all the boom stuff in Chisel, BlueSpec, System Verilog descriptions. And as Nikhil told everybody yesterday, the ISA Semantics Working Group has mechanized RISC-V semantics in a bunch of ways, some traditional and some a little bit unusual. And those include several Haskell implementations and mechanization in some logical frameworks like Coq. So this is a lot of different definitions for the same set of ISAs. And all of these different definitions raise a pretty important question, and that is, how do we provide assurance about the definitions and also anything that somebody builds based on those definitions? So when I say assurance, what I mean is basically, if I want to provide assurance about a computing system, I need to prove two different things about it for some definition of the word prove. Right? If you want a little bit of assurance, you can do something a little bit convincing. If you want high assurance, probably what you want is mathematical proof. So the first thing is the system does what it's supposed to do. Seems pretty obvious, right? And of course, what it's supposed to do could be specified down to, at every single cycle, it's supposed to do these particular steps. Or it could be specified at the level of inputs and outputs, right? I provide input to this RISC-V program, I run it, it's supposed to spit this output out. The level at which you specify that has effects on how you provide the assurance you want. But importantly, it also means you need to show that the system doesn't do anything that it's not supposed to do. And this is the part that actually gets ignored fairly frequently. And this is what results in a lot of the sort of security problems that you end up seeing where you have unintended side channels that leak information, or other sorts of exploits. So that second one is often overlooked when people say, oh, my system works, I verified it, I validated it. Often they're talking about just number one, not so much number two. So let's say that you hand me an implementation of a RISC-V processor, and it claims to be RV32i. How do we actually know that it really is RV32i? Well, typically what we do is we run a lot of conformance tests. And there are several really good sets of conformance tests out there. But that is a little problematic, because if you're looking for high assurance, now those test writers have a really big burden on their shoulders. Now they need to show that the conformance tests cover everything that could possibly happen, and that they're really testing for what I'll call RV32i-ness, right? Like, do the conformance tests actually match those other definitions of what RV32i means? It also doesn't take into account number two from the previous slide, right? You could pass an entire suite of conformance tests and still have an implementation that does something you don't want, like leak a bunch of private key information out of a side channel, or otherwise have security flaws. So what we think a better answer is let's formally verify these things. So one example of this, which you heard a little bit about yesterday, let's say we have one of these Haskell specifications, formal specifications of RV32i. We compile it using the clash tool, and we get out Verilog RTL on the other end. And then we use equivalence checking tools for Verilog to take that RTL, which came from the Haskell formal spec, and relate it piecewise to the RTL of whatever RV32i you actually want to get assurance for. This is done both with commercial tools, things like Jasper Gold, and open source tools like Yosis. And in fact, this is exactly what Clifford Wolf is doing with his formal spec of RISC-V. And he's going to talk a little bit more about formal specs and some of the holes in them after the break. And I encourage everybody to pay close attention to that talk as well. And we're doing it with Jasper Gold, and we're also going to try to use any other tools that we can get our hands on to sort of push those tools and find out how much of this actually is practical with the tools that are out there right now. So you may be thinking to yourself, OK, great, but that doesn't sound feasible to actually do that for a full-size processor. And you're right with current technology. So equivalence checking for some small implementation of a shallow pipeline in order, just core RISC-V implementation with no extensions, is a reasonably straightforward thing to do. Clifford's done it. It's great. But doing it for deep pipeline processors, multi-threaded, out of order, with a bunch of different extensions, maybe custom designs for some parts of the processor, maybe custom extensions, totally different ballgame, right? And this is not helped by the fact that equivalence checking tools, like the ones I'm talking about, really only exist for Verilog and System Verilog. So if you happen to like writing in a higher level language, which I hope you do if you're writing something that complicated, then you're a little bit out of luck, because you can't really reason about your higher level language. Instead, you actually have to reason about the Verilog that gets spit out by the compiler for the higher level language. So that's an unfortunate thing to have to do. So what we're doing as mostly part of this DARPA project focusing on system security, but also just for our own research and development, is taking Galois' experience in formal methods applied to software and seeing how we can apply them to this hardware domain. And what we took a step back. We said, OK, what do we need to do? Well, in order to reason about a RISC-V, you need good machine-readable specifications, not just for correctness, but also for security, right? Actual mechanized security requirements that you can actually take and compare to an implementation and say, yes, this implementation has no side channels, or does not expose this encrypted information to this part of memory at this time. You also need a way to actually measure the conformance of whatever implementation you're getting assurance for to these specifications. And you need to actually have reasonable ways to work with these measurements, because nobody actually wants to just sit and look at a screen full of math and numbers and say, what does this mean about the implementation that I just wrote? In other words, we want people to actually use these technologies once we develop them. We don't want them to sit in a lab somewhere and have nobody use them. So for correctness specs, Nikhil talked some about this yesterday, but we have a bunch of different specs of a bunch of different kinds, and different levels of rigor, and different levels of completeness. So there's the very nice set of RISC-V executable tests from the foundation. There's Clifford's reference Verilog implementation. There's Thomas's RISC-V semantics in Haskell, which he talked about on Monday at the tutorials. There's Nikhil's RISC-V semantics in Haskell and also in BlueSpec System Verilog. There's the one from SRI in L3. There's the one in SAIL from Cambridge, which I didn't mention on this slide, mainly because I couldn't find a public link to it or anything. And then there's ours in Haskell, which is not available publicly yet because we're not done with it and because we have to ask permission to make it publicly available first. But we will. We plan to. So that's a lot of specs. How do you use those effectively? And is one better than the other? And for what applications is one better than the other? Well, one thing you can do is do rigorous validation through executing these specs. Most of the specs themselves are executable, and certainly the artifacts that you want assurance for are executable. So you can do, of course, ad hoc testing. I'll give you a little bit of assurance. Write some programs, execute those programs on your semantics, execute those programs on your chip, see that they give you the same result. You can do coverage analysis for simulations. So you have properties that you want to prove about your mechanized spec. You translate those into a test bench in an automated fashion, and then you measure the coverage of those properties across validation runs. And you can do bisimulation, where you actually take 2 or 3 or all of those specifications, and you run them at the same time, and you compare their behavior at individual points of the execution. So this is what the BlueSpec RISC-V Verification Factory does, and this is also a fairly common method of doing this in other contexts. You can also do verification, where you use formal reasoning instead of running the thing to actually tell you that it does what it's supposed to. So one thing you can do is turn your test benches into verification artifacts, and instead of running them on your chip, you formally reason about them, and you prove that given this particular mechanized ISA, this test will always pass. So you don't actually run the test, but you prove that it's going to pass because the ISA doesn't admit failure of that test. You can do verification coverage analysis similarly. And you can do bisimulation in a verification sense, where you prove the equivalence of 2 mechanized representations as an equivalence relation over traces. So that is how you deal with correctness properties. Security properties are a little bit different, because security properties often take the form of, this bad thing should never happen. And it's very hard to prove that sort of thing a lot of the time. And it's definitely hard to specify that. There really is no canonically accepted way of specifying security properties in general for hardware systems, or software systems for that matter. So what we're developing as part of this work is a DSL. It's called Lando, after Lando Calrissian from Star Wars, for reasons having to do with the naming of the DARPA program that we're working on, and also because we just like Star Wars. And Lando is going to let you specify the architecture of a system, and its correctness properties, and its security properties. And in addition to that, we're also developing a RISC-V security test suite, which is going to let you execute a set of tests on a RISC-V implementation to give you some rough measurement of the security of that implementation. That is, some rough idea of what kinds of commonly known vulnerabilities it's vulnerable to or not vulnerable to, and evaluate coverage in that way. And this security test suite at least will partially become public. We're going to release as much of it as DARPA lets us release, so that everybody can benefit from that. So that's great, but once I actually have my design specified in this language, in order to make some use of that, I need to measure it. I need to be able to tell what kind of trade-offs I'm making. I might get the best security in the world, but if it causes my power budget to explode, then that's not going to be practical for actually building a real system. So we need metrics for these things. And metrics for power, performance, and area obviously are already existing and pretty widely accepted in the industry. Metrics for security are new, and that's some of the stuff that we're working on now. And basically, what we want to do is take all of these measurements of a given system and present them to the system designer in a way that lets them make intelligent trade-offs. Like, well, I can spend a little bit more power and get a lot more security. Or I could spend a little bit less area and reduce my security by a little bit, but maybe that's okay for the application I'm developing this thing for. And there's going to be a wide spectrum of these sorts of trade-offs. Of course, once you introduce a bunch of new metrics and measurements, you again don't want these to just be, well, you scored a 10 for security, 15, 27. We want to actually have people be able to understand and to explore the effects of their design choices and their implementation decisions on these various aspects of their system. So we're going to be developing a dashboard, which is a visualization of a design and its implementations and their critical characteristics in a way that would make Edward Tufte proud. Basically, nice, visual, intuitive, you can manipulate it, you can play with it, it's going to be great. I don't have a picture of it here because we haven't finished designing it yet, but we will. And we want to take advantage of the idea of product line engineering. How many of you have ever configured a Linux kernel? It's a small handful. So those of you who have, you have already taken advantage of product line engineering. Product line engineering basically is you have a bunch of different features of your project, and when you flip one of them on, it affects what other ones have to be on and which ones have to be off and what, So we want to view hardware designs as product lines, and we want to have a tool for exploring and reasoning about product lines derived from a formal model and automatically generate the feature models for these things, which basically means, let's say that the Pulpino developers, just to pick one that I've looked at in the past, want to look at the Pulpino as a hardware product line. Well, you would actually take all of the Verilog and system Verilog and documentation for that, feed it into our system. Our system will then spit out information about, here are all the different configuration points that I found in that system, and here is how they relate to each other. And now you can view them as a feature model, something like this. So this is a feature model for a very, very small, secure CPU that we developed as part of an earlier DARPA project. And so you can see we have, well, we want to develop a secure CPU. We need to pick an ISA. There's some parameters here. We could do 32 or 64 bits. We could do the RISC-V instruction set or maybe the ARM instruction set. If we pick RISC-V, we have a bunch of different implementation choices. We could go Piccolo or Rocket or RISC-V or Boom. And then for security, we could do a tagged architecture and have a certain size of what our tags are going to look like. Then we can say, well, what's going to be tagged? Is it going to be just the DRAM, registers, data cache, instruction cache? We could also just pick some kind of basic cryptographic assurance. Is it going to be hardware or software based? Is it going to be formally verified, unverified? Is it going to be a symmetric cipher? How big is the key? How big is the block? Which algorithm is it? And so we have this entire space of all the different configurations you could pick for this particular secure CPU. And when you make a choice, like if I pick with 32, that is going to restrict some of the choices I can make down here. If I pick RISC-V, now I absolutely have to pick one of these things because I need a concrete realization of RISC-V. So this happens to be how we configured it in the particular project we did. Right? We did a 32-bit RISC-V based on BlueSpec's Piccolo. We used formally verified hardware cryptography with the AES 128 cipher. And that is not to say that these other choices wouldn't have also been awesome. We just didn't choose them in the couple months that we had to work on this project. But this is the kind of thing that we're going to enable for bigger projects as a result of our work. So the current status of all of this, probably you're wondering, OK, that sounds great, but it also sounds kind of like Fantasyland, right? So right now, we are in the early stages of development on the DSL. We expect that there will be an initial version of the DSL probably publicly available before the RISC-V Summit in December. The security test suite we've already developed some of, but it still needs a bunch of work. Metrics and measures, we are going to try to use as many existing open source and commercial measurement tools as we can because we don't like reinventing wheels. So we're evaluating those, and if you have a tool that measures power, performance, or area that you think we should look at, please come talk to me. For security, we're taking all of the work that's been done on security metrics by NIST, by MITRE, by other sort of government and technical committees and companies, and trying to synthesize that into a single coherent set of metrics. And we expect that to be mostly done by the time that the DSL is done as well. The dashboard, we're starting to work on user interfaces based on our previous work on software dashboards. And the feature model generator, we're in the stages of design for right now. And sort of the big open challenges in this work are accuracy of measures. You know, it's no good presenting people with trade-offs if those trade-offs don't reflect reality. Evolution of security metrics. The field of security metrics is really, really primitive right now, and pushing that forward is a lot of work. And in some cases, it's not clear what is possible and what is wishful thinking. And we would like to integrate more of the tools that people already use on the back end of the system we're developing so that people get to keep doing the things that they're already comfortable doing. They just get to do them more effectively. So again, if you have tools or know of tools that you think we should be looking at, definitely let me know. And that is basically all I have. I also apparently have 45 seconds. But we do have a break coming up, so maybe they'll give me a little flexibility in answering questions.
What is a tagged computer architecture? What are your slides?
Tagged architecture. Yes. So tagged architectures are an approach to security in in processors where you tag regions. Well, one approach is you tag regions of memory with maybe something as simple as a single bit that says this region of memory contains what is supposed to be secure information versus insecure information. And then as data flows through the processor, you check as that's happening to make sure that data doesn't flow from regions that are tagged secure to regions that are tagged insecure. So it's way more complicated than that, and I don't actually work directly in that area, so I can't do it justice. But there are people here who do work directly in that area, and I can talk to you offline more about that and point you to them.
Just describe the capability.
So essentially what it does is it lets you prevent some of the bad information flow things that result in security problems. So if something bad were going to happen, information was going to escape, the processor would trap instead of letting the information escape, and it would halt your system, for example. Oh, you can ask one if you've got one.
Formal verification methods or tools such as Jasper Go is a good way to verify our implementation. But typically, we gather bounded proof rather than full proof. So what do you think about this, and what's your suggestion to?
So if I'm understanding the question correctly, are you asking what I think of the current technology that's out there for this? So one of the things that puzzled me when I went, until recently, I only did hardware. I did hardware work in the late 1990s. And one of the things that really kind of puzzled me when I came back to doing some work in hardware a couple years ago is how little had changed in terms of the state of the art for verifying things and sort of doing assurance since the late 1990s. So tools like Jasper Gold are good things, but we're currently actually, part of our work is trying to figure out how far we can push those tools to achieving the kinds of assurance goals we want to achieve. So the short answer is, I like the fact that the tool exists, and I know it can do some good things, but I don't know how much of the problem it actually solves. And one of the reasons for that is that nobody is actually willing to tell us how the tool works or what it does inside. So it's really hard to tell. And so that's part of what we're doing, is evaluating what's out there to see what we can use and what needs to be built.